The majority of chemical reactions during stellar evolution, mind you, establishment science, they want you to believe that stars are nuclear, so they completely ignore chemistry. That stinks. I feel sorry for them, because it means they don't understand the stars at all. You can't ignore chemistry when you explain star evolution. For this talk, I'm going to go over water, okay? Alright, this would be a synthesis reaction, as well as exothermic. You have one bond connecting the hydrogens, and then you have a double bond connecting the oxygens. And when these combine, they make water. Now if you can see it, those are 3 bonds, 1, 2, 3. And when they combine, it will release energy because it has to create another bond. So you have 1, 2, 3, 4 bonds. The formula for explaining this in kilojoules per mole is pretty basic. I'll try my best to explain it without confusing anybody. Alright, so you start out Alright, this is where you start, okay? This equal sign is going to carry down right here. Now, this is the change in heat, okay? This is the double hydrogen, or the hydrogen bonds. There's 2 bonds. This is the 1 oxygen bond. And this is the product, the end result. So remember, you had the 4 bonds in the end result, and you had the 1, 2, 3 bonds in the beginning. So this was one of the reactions. This is the beginning, and then you have to add this, which is the end result. And you add them together to see if you have a net plus or negative heat loss, okay? So you just plug in the numbers for this. So you have 2 times 436 kilojoules per mole plus 1 times 498 kilojoules per mole. Okay, this is the energy right here. This is the energy of this. Okay, you can just go ahead and stop this video and pause it if you want just to look it over. But this is the energy per bond for those hydrogens, and this is the energy per bond of that double oxygen bond, okay? So you take all that, and then you subtract this, okay? So this right here would be minus 467 kilojoules per mole. Okay, this is this down here, and this right here is this. Okay, so you're basically finding out how much energy in these bonds and how much energy is in these bonds, and you find the difference between the 2. And if you plug the numbers in, what you'll get is negative 498 kilojoules per mole. if the end result is a negative, you have an exothermic reaction. Meaning the heat of those bonds was subtracted, meaning the heat had to go somewhere else. Now, if this number was positive, it means the reaction was endothermic, meaning heat absorbing. So since to create water from hydrogen gas and oxygen gas to the water molecule right here, since that is exothermic, we have to look at the Earth's oceans and realize something very important. To create the Earth's oceans, the Earth had to have somehow combined all that oxygen with the hydrogen, releasing an incredible amount of heat. And I go over that in another paper. But for this talk, two very important points I want to make up, or talk about, after all that was, there are basically two factors which determine whether a gaseous reaction will be exothermic or not, okay? Those two factors are the relative strength of the bonds as measured by the bond enthalpy. Okay, what this means, here I'll go ahead and write the second one. The second one is the relative number of bonds formed and broken. All right. What this means right here is essentially you have, remember in the previous example you had hydrogen connected to hydrogen. This is one bond. Now it has a specific strength to it. Now with the oxygen, remember, you had the relative strength of a single bond and then you have a double bond right there, meaning this bond strength is stronger than this. And sometimes you'll find bonds, maybe, no, I think nitrogen maybe. You'll have a bond like that, and you'll have a triple bond, and this is really strong. Now, as well, single bonds can actually have different strengths as well. Like a single bond between oxygen could be different than a single bond between hydrogen. So that's bond enthalpy. You can look up these kinds of things, and their bond enthalpies on the IUPAC site, where they have a lot of chemistry information, and hyperphysics, they have bond enthalpies listed there. But look at those things, because when a star evolves, all that gaseous matter is going to form bonds via synthesis reactions, okay? And you can measure how much heat those are going to release when they combine and make larger molecules by the bond enthalpies of those materials. And they can get really, really complex over time. And yes, so complex that they literally become life itself. So that's the top part. And the second half of this is the relative number of bonds formed and broken. As you remember with the first one, you had two hydrogen bonds, or two hydrogens connected, and then you had an oxygen, okay? With this, you break 3 bonds. You break 3, 1, 2, 3, and then you form form 4 of them. 1, 2, 3, 4. Meaning, if you broke 3 and then you formed another one, it had to be exothermic. For the most part. I mean, there are exceptions, but basically that's a good rule of thumb. is if you make more bonds than you break, the synthesis reaction is going to release heat. All right, I think that really sums it up. I'm going to go ahead and list some more chemistry things on there, and keep in mind that when I want to talk about these things more because astronomers and astrophysicists, they don't like to talk about chemistry. They say a star is a fusion reactor, there's no chemistry going on, yet we have electric currents in the sun, we have magnetic fields, we have heat, thermodynamics, and we have solar wind. Solar wind is direct evidence for chemical reactions. It's called chemical heterolysis. I went over that in a previous talk. But I'm going to go ahead and link a whole bunch of stuff to the bottom, and if you have any questions or comments, please leave them below.